Hello friends, welcome to Susan and John MathTube. In this video, we are going to continue our discussion on Gauss Divergence Theorem. Now remember, in the last video, we learned how to deal with Gauss Divergence Theorem. Now look at this. Why I am teaching you Gauss Divergence Theorem directly is, when you verify Gauss Divergence Theorem, you will be learning how to evaluate surface integrals and you will be learning how to evaluate volume integrals at the same time. Anyway, if you want to make things more clear, after watching these videos, you can learn them separately from any book you like. Anyway, for those students who did not watch the last video, I will strongly recommend pause this video right now and watch the cube problem in Gauss Divergence Theorem. And remember one more thing, if you know how to solve the cube problem, you will be capable of solving the cuboid problem and the parallelly piped problem for Gauss Divergence Theorem as well as surface integral problems. Okay, now in this video, I want you to focus on the cylinder problem. Okay, so please write the question. Verify Gauss Divergence Theorem. For the vector function, so please write it very carefully. 4x times I minus 2y squared j plus z square times k taken over the region bounded by the cylinder x square plus y square equal to 4. Wait a minute. They said cylinder but they are giving you a circle. Oh, okay, that makes sense. A cylinder is made up of many circles arranged one above the other. Okay, just imagine a cylinder is made up of many circles. And if it is an infinite right circular cylinder, the equation of a cylinder and the circle will look alike. But wait a minute, they have given more things. They have given that z varies from 0 to z is equal to 3. So they have defined the height of the cylinder. So you can imagine we have the XYZ axis. So let's say this is the X axis, this is the Y axis, and I can see the circle in the XY plane. And you keep on making circles one above the other until you reach a height of 3 units. Okay, so the first thing to do, we are not going to worry about the cylinder. We are going to write the Gauss Divergence Theorem. So that is very important. In examination also, don't forget to write the statement. Anyway, I am going to make it short, but it is better to learn the statement properly so that you get that 1 mark, because now and then they ask, state Gauss Divergence Theorem. It will be for 1 mark. If you write it in your own words, that is okay. And if you write just like what Gauss stated, that's the best. But if you create your own theorem, no, they are not going to give you marks. Okay, anyway, by Gauss Divergence Theorem, double integral f dot n ds, that is a surface integral, will be equal to triple integral divergence of f dv, that is the volume integral. Okay, so this is what I told you earlier. The reason I have not kept separate videos for surface integral and volume integral is, when I teach you Gauss Divergence Theorem, we are going to deal with both. We are going to learn how to evaluate surface integrals and we are going to learn how to evaluate volume integrals. And later, after watching these videos, you can take any book you like and work out a lot of problems and clearly understand surface integrals and volume integrals. And one more very important thing, sometimes in your exam they may not ask you to verify Gauss divergence theorem. They may simply ask you to evaluate a surface integral. At that time, don't be foolish and evaluate all these things. And if they ask you, use Gauss divergence theorem and evaluate some surface integral, don't verify it, just find the right hand side, that will be more than enough. Okay, now let's move into the problem. So they have given you a cylinder. Okay, now let's go and check the cylinder. Okay, here we have the cylinder. Can you see the red circle at the bottom? It is a circle of radius 2 units. And you can see that the cylinder is made up of many circles, and it varies from 0 to 3. I hope you are able to see. Okay, and our cylinder has 3 surfaces. The green one on the top, the blue color curved surface, and the red color at the bottom. So we have 3 surface integrals to evaluate. So basically evaluating the surface integral means top surface plus the curved surface plus the bottom surface. Okay, and volume integral means you are concerned with the part inside, that like what you call, you can see the cylinder, the inside part is the volume integral. Okay, so let's go back to the problem. I'm going to evaluate the right hand side first. So basically remember, surface integral means we have the top green color circle, and surface 2 means the curved blue color surface, and surface 3 means the red color bottom, the circle again. So we have to evaluate 1, 2, 3 surface integrals if you want to evaluate this. And again we have to evaluate 1 volume integral. Okay, let's stick to the right hand side. So I'm going to write to evaluate triple integral V divergence of f dv. Okay, so what is f? F is 4xi minus 2y squared into j plus z squared into k. I hope you remember divergence from your second semester. So divergence means del dot f, dou by dou x of the I component plus dou by dou y of the j component plus the partial derivative with respect to z, the k component. And that gives us divergence of f is equal to, I am sure you are good in differentiation, you are going to get 4 minus 4y plus 2 times z. Okay, now look at this. To evaluate the volume integral in a cylinder, it is very easy. First of all, you should imagine that circle. What is the special? Okay, I'll do one thing. I'll draw our x-axis and y-axis. And I'll draw that circle you saw there, the base circle. I'll show you. The circle, the red color circle you see on the bottom. This is exactly what I'm drawing. Can you see? This is exactly what I'm drawing. I'm not worried about the height part now. I'm just drawing the circle. Can you see the x-axis, y-axis, this circle? This is what I'm going to draw. Okay. Now, what is the radius of the circle? 2 units. So this is 2. This is x equal to minus 2. Now, I hope you remember multiple integrals from second semester. So, I want to cover the entire region. I want to cover the entire region of this circle. So, it is obvious that x varies from minus 2 to 2. Do you remember the slider that I told you in multiple integrals in second semester? See, the slider starts from minus 2 and the slider keeps on moving, keeps on moving, keeps on moving till we reach 2. So clearly x varies from minus 2 to 2. Now we have to find the height of the slider. You can see that the slider touches the circle in the negative part of the y-axis to the positive part of the y-axis in the circle, of course. It starts in the negative part of the y-axis. It starts below the x-axis to above the x-axis. Now look at this. The equation of the circle is x square plus y square equal to 4. So y squared is equal to 4 minus x square. So y is equal to plus or minus root under 4 minus x square. So the bottom part means below the x-axis means y will be controlled by minus 4 minus x square to the upper limit 4 minus x square. Okay, so that settles the circle. That means now I am capable of covering the entire circle. Now do you remember I told you our cylinder is made up of many circles. It starts from z equal to 0 and it keeps on moving up till it reaches the green color circle at the height 3. So I am going to write z varies from 0 to 3. I hope you are able to understand the limits. Okay, now let's go for the right hand side of Gauss Divergence Theorem. So right hand side in my statement is triple integral. I'll write x equal to minus 2 to 2 and y varies from minus root under 4 minus x square to root under 4 minus x square. In your exam write neatly. Now right now I'm writing in a very messed up manner. So 4 minus 4y plus 2z, inner integral is dz, then dy, then dx. Okay, so same logic from second semester. You have to evaluate the inner limit, inner integral. So that is with respect to z. So we are going to integrate with respect to z, and when you integrate with respect to z, z will be the only variable. That means x, y, everything else. So this whole thing is a constant. Are you able to see that? So constant integrated with respect to z will give you constant times z plus 2 into z. What is the integration of 2 into z power 1? It will be 2 into z to the power 1 plus 1 by 1 plus 1. So we get z square. And the limit is within 0 to 3 dy dx. Now let's plug in the limits. X equal to minus 2 to 2. Integral y is equal to minus root under 4 minus x square to plus root under 4 minus x square. So you can plug in upper limit. So when you plug in upper limit minus lower limit, you can see that we get 4 minus 4y into 3 minus 0. Plus when you plug in upper limit minus lower limit here, you can see that you get 9 minus 0. Okay, so that's not a big deal. You can simplify that easily, dy dx. So let's go for the next step. So in the next step, we are going to distribute this 3. So we're going to get 12 plus 9, that will be 21. So you're going to get 21 minus 12y dy dx. Okay, now comes the next hero. So time for integration with respect to y. Okay, so we're going to get x equal to minus 2 to 2. Okay, tell me, what is the integration of 21? Actually, if you want, you can use properties, but if I use properties, some of you will be confused. So I'm not going for that. I'm just going for direct integration. I'll repeat, if you know properties of integration, you can do this even faster, but let's keep things very simple. So 21 integrated with respect to y will be 21y minus 12 into y. 12 into y will give you 12 into y squared divided by 2, because y means y power 1. So y power 1 plus 1 by 1 plus 1. So that gives me 6y squared. Within the limits, y is equal to minus root under 4 minus x square to root under 4 minus x squared dx. Now time to plug in minus 2 to 2, 21. Okay, when I plug in upper limit minus lower limit, I can see that it is going to get doubled. Look at this, I'm going to plug in upper limit minus lower limit. They are both same, but they are negative, so it's going to get doubled. So I'm going to write 2 times root under 4 minus x square. Minus, if I plug in upper limit and lower limit, I'll get the same thing, because when you square this negative quantity, you're going to get the same thing, right? So it will be 0. Okay, you can do that patiently. Okay, so I'm left with 42 integral x is equal to minus 2 to 2 root under 2 square minus x square. I think you remember the formula from class 11, 12. Root under a square minus x square will give you x by 2 root under a square minus x square plus a square by 2 sine inverse x by a. So I'm going to apply that formula. So 42 times, if you want, you can apply properties of definite integration. That's completely up to you. Plus a square by 2. So 2 square, 4 by 2, 2 sine inverse x by a within the limits x equal to minus 2 to 2. Okay, now time to plug in the limits. I'll tell you where. I'll mark green. Okay, so I wanted to plug in the upper limit first. So 42 times, when you plug in the upper limit, this is going to be 0, 2 square minus 2 square. Plus it will be 2 sine inverse 2 by 2, that will be 1, that will be pi by 2. Minus, when you plug in the lower limit, again this will become 0, because minus 2 the whole square will give you 0, and this will give you sine inverse minus 1. Sine inverse minus 1 is, minus will come outside, so minus pi by 2. So this is going to be minus 2 pi by 2. So cut. So 42 into 2, that will be 84 pi. Okay, so we are done with one integral. So think about it, you have to evaluate 4 integrals like this, 3 more integrals like this. Okay, now let's go a little bit fast. So let's go to surface 1. So look at this, surface 1 means the surface on the top. Okay, now remember, we are going to evaluate the surface integrals. I'll repeat, we are going to evaluate the surface integrals, and we are going to evaluate double integral S f dot n cap ds. And ds is actually, do you remember what is ds? ds means the value depends on the projection. If you are going to project the surface on the xy plane, for example, look at this. If you project this green stuff on the xy plane, see, can you see the projection? It is a circle. Now, so ds is equal to, if you project it on the xy plane, it will be dx dy the whole divided by mod n dot k. Similarly, if you project it on the yz plane, it will be dy dz. So there are three formulae for this, and you can by heart the formulae. If you project it on the yz plane, it will be dy dz by n dot I, the missing one. You can think about the missing one. Otherwise, it will be dz dx by mod n dot j. You can use any formula you like. Okay, now this n is actually the outward drawn normal. What is n? I hope you remember from the last video, the cube problem. N means the outward drawn normal. Now remember, if the surface is a plane surface, then we may have an advantage. We may not have to calculate this n. But in your second semester, you learned that the outward drawn normal is given by grad phi. Don't forget this. In general, if you want the outward drawn normal to any surface, all you have to do is you have to calculate gradient of the function. Okay, now let's see if we have advantage or not. In cube, we had a huge advantage. I'll repeat, in cube we had a huge advantage because all the 6 surfaces were parallel to the x-axis, the negative x-axis, the y-axis, the negative y-axis, etc., etc. Okay, so let's look at surface number 1, the green surface. It's a plane surface, and that plane surface is parallel to our xy plane, and I think you can see the outward drawn normal, the blue stuff, the blue axis, that is k. So you have a huge advantage here. N cap is equal to k. And for the green part, you know one more thing. You note that the value of z is equal to 3. Think about it. It's a plane surface, right? In the green region, there is no change in height. It is not wobbly or anything. It doesn't go up and down or anything. That z value, the height value is fixed. It is fixed at, look at this, at any point on the green part, the height is 3. It is kind of like standing on the roof of your house. At any point, you are at the same level. I hope you don't have a slanted roof. I mean, a roof parallel to the ground. Okay, so n is equal to k, advantage number 1, and we know that the height is equal to 3. So I can write here surface number 1, the top surface, the surface number 1. And another thing, did you notice it's a circle? So let's calculate f dot n. So f dot n means the given vector. What is the given vector? 4x into I minus 2y squared into j plus z squared into k dot, what is n? K. Oh wow, we have a huge advantage here. Do you know what happens when you take dot product with standard unit vectors? You know I and k are perpendicular, so the dot product will be 0. J and k are perpendicular, the dot product will be 0. And k and k share the same direction, so the dot product will be 1. So we will be left only with z square. Okay, but what is z? So that will be equal to 9. So for surface 1, so I am going to write like this, double integral over surface 1, f dot n cap ds, it will be surface 1, is equal to double integral s1 9 ds1. Now we have the real advantage. The real advantage is 9 comes outside. Double integral of a surface. Now look at this. We know this surface is a circle, right? And you have to understand, okay, if you want, I'll put that formula and show you. This will be actually dx dy by mod k dot k, that will be 1. Actually, this is the area of that circle. Can you see the radius of the circle is 2 units? And the area of the circle will be pi into radius squared. So that will be 9 into 4 pi. So that will be 36 pi. So please note this. For surface 1, double integral f dot n is equal to 36 pi. Okay. Now let's do the next job. Let's go for the easiest job. Let's go for surface 3, the bottom circle. I'll show you the bottom part, this one. Okay, can you see the outward drawn normal? Can you see the blue axis coming outside? Oh, that is the negative z axis. You know that z axis controls height and depth, right? So at the bottom, n cap is equal to minus k. And the height of the circle is fixed at 0. Okay, so we have a huge advantage here. F dot n cap is equal to 4xi minus 2y square into j plus z square into k dot minus k. I told you, when you take dot product with standard vectors, this will be gone, this will be gone, only this part will remain, and there is a minus, so it is like minus z square, but z is 0, so this integral is going to vanish. So double integral surface 3 means the bottom surface, f dot n cap is equal to 0. Now let's go for the hard part, that is surface 2. Surface 2 is the curved surface. Curved surface means we are in big trouble, because point to point, look, point to point, the normal will be different. Point to point, look, at this part you can see the outward normal is the red color axis, our x-axis, so it will be I. And here the outward drawn normal will be minus I. Here the outward drawn normal will be j. Here it will be minus j. So point to point, the outward normal to the curved surface is different. So we have to go for grad phi. So let's write S2, the curved surface. So the curve is given by x square plus y square minus 4. You might remember how we make the curved surface into a function. Okay, so we took the cylindrical surface. Now I am going to calculate grad phi. Grad phi means the normal vector, and that will be I partial derivative of phi plus j partial derivative of phi with respect to y plus k partial derivative of phi with respect to z. So we get I 2x plus j 2y plus 0k. We need unit normal vector, so that will be, you know how to make a vector in unit normal vector, right? Divide throughout by the modulus by root under 4x squared plus 4y squared. So n cap will be 2 will come common, xi plus yj by 4 will come common, it will come outside the square root as 2, and root under x square plus y square. X square plus y square is 4, right? The curve. So this will be 2 into 2. So n cap is equal to xi plus yj. Okay, now we are going to evaluate f dot n cap ds2. So this will be f dot n cap. F means the given function 4xi minus 2y square into j plus z square into k dot, oh I forgot, divided by 2. There is one 2, right? Yeah. So xi plus yj plus 0k divided by 2 ds2. So that will be double integral s2. How do you take dot product? Yeah, 4x into x will be 4x squared minus 2y cube. So that will be equal to 2x square minus y cube ds2. Okay, now I'll tell you one very easy method to do this. It's to convert into polar. Okay, it's 3 dimensions, so we will convert it into cylindrical coordinates. So cylindrical coordinate means, you know, the cylinder is a circle of radius 2. So x equal to radius will be 2 cos theta. It will be just like polar. It will be just like polar, but you have to additionally give the coordinates of the height. You know the cylinder varies from 0 to a height of 3, right? Okay, and remember theta varies from 0 to 2 pi. That is the only way you can cover the entire circle. Okay, so let's convert it. So we will have two variables. Theta varies from 0 to 2 pi and z varies from 0 to 3. And the differential you have to remember from multiple integrals. It is given by r dr d theta, and here it will be r into what are the new variables? dz d theta. So it will be 2 into what is x? 2 cos theta. So remember, like what you call, all these comes from multiple integrals, and this is the cylindrical substitution. So 2 into 4 cos square theta minus 8 sin cube theta, and the differential part will be given by 2 times dz d theta. You should remember r into the new variables, differential of the new variables. Okay, so now it's very easy. You can you are going to integrate with respect to z. So when you integrate with respect to z, look at this, the whole thing is going to be constant. All these things will be constant. So 2 goes outside, 8 comes common, so we have 16 here. Integral theta is equal to 0 to 2 pi cos square theta minus sin cube theta. So this is a constant. So when you integrate with respect to z, it will be like z within the limits 0 to 3 d theta, and that will be 16. Theta is equal to 0 to 2 pi cos square theta minus sin cube theta, and it will come 3. So I'm going to write it outside, d theta, and the remaining part you can integrate yourself. For cos square theta you can convert it into what you call half into 1 plus cos 2 theta. The video is already long, that's why I'm going to stop it right now. So you'll end up with 48 pi. You'll end up with 48 pi. So the total integral on the left, f dot n cap ds, will be We did it with surface 1, we did it with surface 3, and we did it with surface 2. So that will be 36 pi plus 48 pi plus 0. You can use the calculator and do the addition, or just add 40 and subtract 4. So that will be like 88 minus 4, that will be 84 pi, which is equal to the left hand side. Okay, so it's a long one. So this is how we deal with cylinders. Okay, to increase your confidence, I'll give you one more question, and I want all of you to try this one also. So we have a function f is equal to yi plus xj plus z squared into k, and the cylinder is given by x square plus y square is equal to 9 with a height 0 to 2. So you have to verify Gauss Divergence Theorem. For one last time, let me tell you the advantage of Gauss Divergence Theorem. When you are verifying Gauss Divergence Theorem, you are actually learning how to evaluate the volume integral, and you are also learning how to evaluate the surface integral, because you are doing a verification problem. Okay, so the first thing to do is you have to write what we call double integral over S f dot n cap ds is equal to triple integral volume divergence of f ds. And you can evaluate the right hand side. It's very easy. What will be the limit? X will vary from minus 3 to 3. Y will vary from here. You can get it from the circle. 9 minus x square to positive 9 minus x square. And of course the height is given by 0 to 2. And the integral value will come 36 pi. So remember, the answer is 36 pi. Okay, and for the surface part, you have to understand a cylinder has 3 surfaces: the topmost, the bottom, and the curved surface. The top and bottom are very easy to evaluate, because you know the outward normal on the top is k and on the bottom it is minus k. And in such problems you have a huge advantage. You have z equal to 0 here and the normal minus k here, and here z is equal to 2 and the normal is k. And I will read the values on the top and bottom. On the top we are getting 36 pi, and on the bottom it is 0. And now one very important thing, for the curved surface you have to calculate gradient of phi, and gradient of phi turns out to be 2xi plus 2yj. So you can evaluate the rest. The answer comes to be 0. Anyway, you have to get the sum to be 36 pi. Okay, go through the video. There will be a lot of confusion. It's a like what you call extremely high quality mathematical problem. Anyway, if you have more doubts, you can message me or put on the comment section. Okay, so I'll be back with the next video very soon. So till then, my friends, bye.